Hi, I am Varun Joshi and welcome to day 31 of our Certified Kubernetes Administrator 2025 course. It is part 1 of our TLS in Kubernetes Masterclass. Today we are laying the foundations, understanding how TLS works, what public, private and self-signed certificates are, and the basics of mutual authentication. So let's get going. Before I start this lecture, I want to explain who is the client and who is the server. A client is the one that initiates a request. The server is the one that responds. Extremely simple definition. So if Varun wants to download something from his S3 bucket, then Varun is the client because Varun is the one who is initiating the communication, and S3 bucket is the server because it is S3 bucket from where the files will be downloaded. When Seema is accessing pinkbank.com to, let's see, check her balance, then Seema is the client because she is the one who is initiating the connection, and pinkbank.com becomes the server because it responds to her request. In this scenario, it gets a little more interesting. When Seema wants to know what all pods are running in her cluster, she runs the command kubectl get pods. Understandably, as Seema is the one who is initiating this request, Seema becomes the client, and API server is the one towards which Seema has sent this request. So the API server becomes the server. But this information of the pods that are running in the Kubernetes cluster is not with the API server. API server will in turn initiate a connection to etcd to know what all pods are running in the cluster. When API server initiates the communication to etcd, API server becomes the client and the etcd data store becomes the server. So in totality, in this connection, API server acts as a server as well and also as a client. So whether an entity is a client or a server depends on who is initiating the request. It is the client who initiates a request and the server is the one that responds to that request. Now let's see public key cryptography. Public key cryptography is widely used by application layer protocols for security and secure key exchange. And these protocols are not just limited to SSH and HTTP. There are other protocols like FTP Secure, SFTP, IMAP, SMTP that use public key cryptography behind the scenes for authentication and secure key exchange. But as DevOps engineers, you will be widely working with two key protocols of application layer that are SSH and HTTPS. I want to discuss SSH keygen and OpenSSL. These are tools that are used for key pair generation. So first, let's look at SSH keygen. We also saw a small demo of SSH keygen in our previous lecture where we generated a public private key pair for SSH authentication. Private keys stays with the client and the public key is on the server, and we'll dissect this as we move along with this lecture. Now, it is not just SSH keygen that is the tool that you can use to generate SSH keys or key pairs. You can also use PuttyGen if you are on Windows and OpenSSH with Unix based systems. Having said that, SSH keygen is a popular tool that is used to generate SSH key pairs. Now I want to discuss about the formats. There is a public key and then there is a private key. Public key will usually have .pub as an extension, and private key will have key in the name, or it might not have any extension. If you remember in the last lecture when we generated an ED25519 key pair, the private key did not have any extension. Now let's discuss OpenSSL. Firstly, I said that we are going to discuss SSH and HTTPS protocols. But here I have mentioned TLS, not HTTPS. When I talk about HTTPS, the S stands for secure, hypertext transfer protocol, secure. And the secure part is there because there is TLS that is working behind the scenes to provide both authentication and secure key exchange for HTTPS. Now, a lot of students think that TLS is something that is exclusive to HTTPS. It is not like that. Other application layer protocols also use TLS protocols such as SMTP, IMAP. They all are using TLS behind the scenes. So it is incorrect to say that TLS is exclusive to HTTPS. So we will be discussing OpenSSL. OpenSSL is a utility that can be used to generate TLS certificates. Now, what are TLS certificates? How they are used? We have already discussed this in the previous lecture, but in this lecture as well, as we move along, we'll be discussing TLS certificates throughout. The tool that is used to generate TLS certificates is called OpenSSL. But Varun, shouldn't it be called OpenTLS? Why is it called OpenSSL? Firstly, SSL is a predecessor of TLS. So previously SSL was widely used. SSL stands for Secure Sockets Layer. TLS is a successor of SSL. It is an enhanced version, and right now TLS 1.3 is the latest one. With SSL, you used to use OpenSSL as a tool to generate SSL certificates. But as time progressed, TLS was introduced and OpenSSL as a tool also matured. So now you can use OpenSSL to generate the latest and greatest TLS certificates. So let's see what are the pointers for OpenSSL. Generates a private key and a certificate with public key, metadata, and CA signature. So here we said that a key pair was generated. Here we are saying that we generate a private key and a certificate, and in turn that certificate has the public key, metadata, and CA signature. CA as in the certificate authority's signature. In general terms, you would often hear administrators say OpenSSL is used to generate a key pair, and that is also right. But you must understand, behind the scenes, it is a private key and a certificate, and the certificate holds the public key metadata, and that metadata is when the certificate was issued, when the certificate is expiring, and a CA signature. The private key secures communication while the certificate verifies the server's identity for clients, and we will see this in a little while. Other tools that can be used to generate TLS certificates are HashiCorp Vault, Cloudflare's SSL, and Certbot. Certbot is associated with Let's Encrypt. Then here are the formats that you would see for TLS certificates. Public keys or certificates in this scenario have an extension of .crt or .pem. .crt is the one that you would mostly see, and like we saw with SSH keygen, the key pairs generated using OpenSSL, the private key will have .key, or it will have key in the nomenclature, or it will have no extension at all. .csr is your certificate signing request. Certificate signing request can be thought of as a form that gets filled when you want your certificate to be signed, and we will look into all this in this 4-part series of mastering TLS. And here the point says public key cryptography underpins secure communication by enabling authentication, that is identity verification, and secure key exchange. First, let's talk about authentication. Here, when CIMA accesses pinkbank.com, then pinkbank.com supplies a certificate, and CIMA, on the other hand, verifies that this certificate is valid and indeed signed by a trusted certificate authority. But CIMA does not provide any certificate. CIMA is trusted by default. So here what we see is called one-way TLS. Only server is presenting the TLS certificate, the client is not. Whenever you access your S3 bucket, it is S3 bucket that provides the certificate. It is not Varun, the client, who presents any certificate. But when we talk about Kubernetes, Kubernetes work on the premise of two-way TLS, which is also called mutual TLS, that is mTLS. So we will see this in detail in the last part of our series, where we'll generate certificate for Seema user so that she can access the Kubernetes cluster. So what happens in Kubernetes is HCD, if it is acting as a server, first will present its certificate to API server, and then API server will also present its certificate to HCD. So when Seema is accessing the API server, the API server will present its certificate, and then Seema will also present her certificate. So here both client and server are presenting their respective certificates. Hence, this is called mutual TLS. But Varun, we understand TLS is fine, but what happens with SSH? In SSH, it is mutual authentication by default. So first the server proves it is what it says it is, and then the client proves it is what it says it is. So for example, if I go back to day 30 and I zoom in a little, then in this scenario, first the Ubuntu VM proves that it is indeed the Ubuntu VM, and then Seema proves she is indeed Seema. So are you noticing one thing? With both SSH and TLS, it is the server that is proving its identity first. Once the server's identity is proven, only then the client is proving its identity. And why is that? Because we do not want clients sending sensitive information to servers that are not trusted. Hence, it is always the server that proves its identity first, be it in SSH or TLS. So remember this point as we progress with this lecture. So what I now want to do is I want to discuss public key cryptography with respect to both authentication and secure key exchange for both SSH and TLS. So let's start with SSH first. SSH mutual authentication. So like I said, both server and client prove their identity. But how do they do so? Let's first understand this diagram. You have AWS cloud here. I have an Ubuntu VM here. And whenever I install any Unix based VM, by default, SSH is installed onto that VM. Similarly, in Ubuntu VM, we have OpenSSH server installed. And whenever OpenSSH server or any SSH server is installed, there are private and public keys generated automatically for all the algorithms supported by that operating system. So for example, let's say if Ubuntu supports RSA, ECDSA, ED25519, then you would see key pairs generated for all these three algorithms. Why they are generated, we'll see in a little while. Then we also have a user Seema here. Seema wants to access this Ubuntu VM. So as step 1, Seema generates a key pair using SSH keygen utility. Once that key pair is generated, in step 2, Seema copies the public key onto the home directory of the user. Seema copies the public key using SSH copy ID, and this public key gets copied into this file which is named authorized underscore keys. Now this authorized underscore keys could have multiple public keys, and hence whenever you run this command, it appends the public key in authorized underscore keys file. Now why Seema copies her public key onto the Ubuntu server? We'll see this later in this lecture, but for now, understand that she copies the public key and the private key remains with Seema. As we know, private key never leaves and private key should always be kept secure. What happens next? So we understand that both server and client must authenticate with each other. So first, let's say Seema initiates an SSH connection. There is one thing that I want you to engrave in your mind. With SSH, the encryption happens at the very beginning. So if you see here, this is the step 1, and step 1 has arrowheads in both the directions, which implies with SSH both Seema and the server participate and they generate something called a session key. Session key can be thought of as symmetric key. If you have any confusions pertaining to symmetric key, you can go back to day 30 and watch that lecture. But with symmetric key, there is only one key involved, and that one key is used both for encryption and decryption. For example, if Seema encrypts something using a session key, then Ubuntu VM can only decrypt if Ubuntu VM has that session key or that symmetric key. But Varun, how is this key generated? What happens is Seema and this Ubuntu VM or the server, they generate a ephemeral key pair. And whenever they generate an ephemeral key pair, they share their public keys with each other, and based on that, a session key is created. This session key is created for both Seema and this server using Diffie-Hellman or ECDH algorithm. ECDH is elliptic curve Diffie-Hellman, and these algorithms are used to generate these session keys. But Varun, they just exchanged their public keys. How can a session key is derived, and you are saying that that session key is same for both Seema and server? How is that possible? I welcome you to mathematical geniuses of Diffie and Hellman. Both of these mathematicians wrote an algorithm that can be used to derive a unique session key based on the ephemeral public key that was generated for both the client and the server. But who is generating these ephemeral keys? The SSH clients, the SSH server, along with the algorithm that you used for generating the session key plays a role. In step 1, the session is encrypted. And once this session is encrypted, any authentication information that flows in that tunnel is encrypted using that session key. Now, understand one thing. The session key is essentially the same session key for Seema as well and for the server as well. And since we have learned that in symmetric encryption, the key must be same for both encryption and decryption. Hence, we know that the key is same. And the important part is Seema never shared that key over the network. Neither the server shared that key over the network. It is the magic of ECDH algorithm that generated the same session key for both Seema and the server. And if we are not sending that key over the network, then there is no chance of that session key or that symmetric key getting leaked. Hence, the possibility of anyone eavesdropping on your SSH connection is near zero. Now, any authentication information that flows between Seema and server is encrypted using the generated session key in this step. We understand that server must authenticate first and only then the client authenticates. But how can the server authenticate? Remember, I told you there is a key pair generated for all the algorithms that this Ubuntu VM would support. Let's say the key pair that Seema generated uses ED25519 as the algorithm. And ED25519 is the default in most Unix-like systems. So whenever CIMA initiates an SSH connection, what the server will do as a first step is the server will share the fingerprint of the public key. So since here we are using ED25519, the algorithm is replaced by that, and the algo placeholder is replaced by ED25519, and then a fingerprint is computed and the fingerprint is shared. If you want to find the fingerprint of a public key, you can always use this command to check that. And once it is sent to CIMA, how can CIMA verify? Because CIMA does not have the public key of this Ubuntu VM. Then how can CIMA verify the fingerprint associated with this public key? What will CIMA do is, there are multiple options that CIMA has. So let's see what all are her options. Host key verification method. So this can be thought of as how can CIMA verify that the public key's fingerprint sent by the server are correct. The first is trust on first use, and you would have seen this prompt a lot of times. The authenticity of this host cannot be established. RSA key fingerprint is this. Are you sure you want to continue connecting? And most of us press yes here. So if CIMA trusts that this is the Ubuntu VM I want to connect, then she can press yes, and that is called trust on first use, and then she can continue with this. And as soon as she presses yes for this fingerprint, the public key associated with this fingerprint is stored in a file known as SSH known host. If you see here, this is my .ssh known hosts file. What you see here is it has two public keys, and these public keys belong to this server. And you see there are two algorithms used here, because I would have connected to this server using the key pair associated with this algorithm ED25519 and a key pair that was generated using ECDSA algorithm. So this is fine. Trust on first use is fine. Second is phone a friend. What does this mean? CIMA calls a colleague who already has access to Ubuntu VM using SSH authentication. That person can log in into the server and then figure out what is the fingerprint associated with this public key. And once he or she figures out the fingerprint, it is told to CIMA, and then CIMA can verify that whether the told fingerprint matches the fingerprint that I see on my screen. That is one way. Third way is out of band management. CIMA can take console of this virtual machine and then see what is the fingerprint associated with the public key. And that is the third way to verify this fingerprint. Fourth is Ansible, and you will see this one used in most of the scenarios. So what Ansible will do is, you can use Ansible as a configuration management tool which can be used to configure your Unix like or your Windows systems. What you can configure Ansible to do is, Ansible can copy this public key and it can paste it onto the known hosts file. If the public key is already there in the known host file along with the identification of the server, and here IP address is the identification can also be the DNS name. Once the public key is here, CIMA will not receive this message, because the identity of the server and the associated public key is already stored in the known host. Known hosts implies CIMA already knows these hosts. The next method is manually preload, and manually preload is, once she's configuring this server, she copies the public key and then she manually adds that in her known host file. That is also one way. The last one is centralized trust models, and this is used by enterprise implementations where you use an open SSH certificate authority for this, and I'll let you read about this if you want to know how this method works. So this is how the server proves its identity, and once that server is in CIMA's known hosts file, any subsequent connections that CIMA makes to that server will not ask for verification. But when will it ask for verification? So imagine if there is a malicious user in between who tries to impersonate this Ubuntu VM, then the fingerprint of that public key will change because that server will have a different public key. Hence, SEMA will receive this message again, and then SEMA has an option to choose whether to continue or to not continue with that connection. But I want you to know one more thing. If you are working in public cloud and you are using ephemeral IPs, then you see the known hosts file also has the identification of the server. In that scenario, if you, let's say, power off the machine and then power it on, if you are using ephemeral public IPs, then your IP will change. Hence, the identification of your server change. Though the fingerprint itself or the public key will not change, but the identification of the server will change. In that scenario as well, you will have to press this yes to continue with that connection. So here we have learned how the server will prove its identity. But how will SEMA prove her identity? What this server will do is server will send a random challenge to SEMA, and SEMA here will have to sign that challenge with her private key. And once she signs this, she sends back that signed challenge to this Ubuntu VM. And since this Ubuntu VM already has the public key for SEMA, which SEMA sent to this Ubuntu VM in step 2, hence this Ubuntu VM can verify that the challenge was indeed signed by the private key of SEMA. And we learned in day 30 that anything that is signed by a private key can be verified by the associated public key. So I hope the whole SSH and this mutual authentication part is clear to you. So what we have seen is, for SSH, we have seen how the session is encrypted and this thing happens at the very beginning. And then we also saw how mutual authentication works. Both server and client proved their identity, but it is always the server that first proves its identity. Let's move to TLS. Here we'll only discuss about one-way TLS because mTLS will be discussed once we move to TLS in Kubernetes section. For now, I want you to understand one-way TLS and how it works with HTTPS. And we already saw this in day 30. So I want to mention a few key points. So what I will do is I'll quickly explain this one more time, and then I'll explain you what the problem is with this architecture. So here we have pinkbank.com, and pinkbank.com has a certificate and a private key. They could have used OpenSSL to generate this key pair. Then there is Let's Encrypt. Let's Encrypt is a public certificate authority that can be used to sign your certificate. So Let's Encrypt certificate authority, let's say they also have a key pair. They have a certificate and then they have a private key. So when pinkbank.com decides that now they want HTTPS, they go to Let's Encrypt CA with a CSR. CSR is a certificate signing request, and this CSR will hold the information about pinkbank.com. And then once Let's Encrypt receives this, Let's Encrypt will verify that pink.com is indeed owned by Pinkbank. And once it verifies, it will sign that certificate with its private key. Now SEMA wants to access pinkbank.com. SEMA has a browser. SEMA sends a request. I want a secure connection. Are you really pinkbank.com? And pinkbank.com, as we know, already has a signed certificate, and this certificate was signed by a public certificate authority named Let's Encrypt. And once she presents this certificate to SEMA, SEMA's browser verifies that it is indeed signed by a valid trusted CA. But Varun, how can this browser verify? What happens is all the modern browsers will have the certificate associated with all the popular public certificate authorities in their trust store. So anything that is signed by the private key of Let's Encrypt or any other popular public CA can be verified by your browsers themselves. It finishes at the browser level itself. So once pinkbank.com presents its certificate that was signed by this private key, your browser verifies that indeed it is pinkbank.com. You can continue with the connection, and then Seema says, okay, I trust Let's Encrypt CA. And why does she say I trust Let's Encrypt CA? Because Let's Encrypt is the CA that signed pinkbank.com's certificate. So Seema says, let's proceed with this connection. So what happens is, browser now creates a session key and encrypts it with the public key of pinkbank.com. But Varun, how does the browser have the public key of pinkbank.com? You remember pinkbank.com shared its certificate in this step. Hence, the public key of pinkbank.com of this certificate is there in the certificate itself. So what browser will do is, browser will randomly generate a session key and then encrypt that session key with the public key of pinkbank.com. And understand, no one in the internet has the private key of pinkbank.com, so no one can really decrypt the session key. So once it reaches here, the session key reaches here, pinkbank.com with its private key can decrypt that message and figure out what is the session key. Now in the entire internet, only Seema and pinkbank.com has that session key, and they can encrypt all their communication using that session key. So this is how it works, and this works good. But this design has a problem. What is the problem? So if this private key gets leaked, whatever this browser is encrypting using the public key of pinkbank.com can be decrypted by the malicious user, because this private key is compromised. Hence, we must find means via which the session key is not shared over the network, because if it is shared in over a network, there is a possibility that someone might decrypt it. You must be thinking, but Varun, it is highly unlikely that this private key will be leaked. But that is not how security teams work. In security, if something is highly unlikely to happen, then they consider that it will surely happen. Hence, this was a loophole in this architecture. So how did we solve this? You remember in SSH, the session was encrypted first, and that was encrypted using ECDH algorithm. And using ECDH algorithm in SSH as well, we were not sharing the key over the network. The session key was generated for both Seema and the server separately. Now with TLS 1.3 and with TLS 1.2 that uses ECDH, we use a similar thing like we used in SSH. So let's understand what is happening here. Here the process still here remains the same. So here is my signed certificate. Browser verifies that the certificate is indeed signed because it has the certificate of all the trusted public certificate authorities. What happens is, Seema says, I trust Let's Encrypt CA. Browser and pinkbank.com now exchange ephemeral public keys using ECDHE. E at the last stands for ephemeral, to derive a shared session key. This derived session key is never transmitted, not even in encrypted form. And once this session key is derived, then in the entire internet, this session key is unique only to Seema and pinkbank.com. Only browser and pinkbank.com share the same symmetric session key. Everything now can be encrypted using this session key. Now, even if the private key of pinkbank.com gets leaked, there is no problem. Firstly, it should not get leaked, but in case it does, then also no one can decrypt the communication that is happening between Seema and pinkbank.com, but Seema and pinkbank.com. So I hope this gives you a perspective how TLS 1.3 and TLS 1.2 that uses ECDH is highly secure. So let's move to the next topic, which is types of TLS certificate authorities. First is a public certificate authority, and then there is a private certificate authority, and third is not essentially a certificate authority, so to speak, but we will talk about what are self-signed certificates. So let's first talk about public certificate authorities. PKI. So anything that you see on screen here, as in digital signatures, key pairs, certificate authorities, all these combined are called public key infrastructure. Next is public CAs are used for production environments and public facing sites, like we have been seeing since the inception of day 30. Then next is trusted by all major browsers and operating system. Not just a public CA. It is not something that you can wake up today and say I'll open a public CA. It's not like that. Public CAs, they have a whole process. They must be compliant to certain compliance standards, and once they are, then only they are trusted by browsers. So here I am saying trusted by all major browsers and operating systems. So DigiCert, VeriSign, Sectigo, so all the browsers, all the modern browsers will have the certificate associated with these certificate authorities in the browser's trust store. Then operates within a public key infrastructure. PKI, like we saw in the first point, includes certificate authorities, certificates, public private keys, and CSRs. So I hope public CAs are understood. Let's move to the next one, that is private CA. Now, not for all requirements you would want a public CA, because not all websites that you use are public facing. For example, let's say if you open an organization and then you are 20 odd people and there is an internal website that only those 20 people access, then you will not go to the burden of contacting a public CA. What you can do is you can have a private CA for that purpose, because you know the audience of your website is all internal. So private CAs are often used for internal applications and infrastructure services, not trusted by browsers unless explicitly added to the trust store. So this is an important part. Let's first understand this diagram. I have app1.internal here. This is my app. The name of my application is app1 and it is accessible in the URL app1.internal. App1.internal has a key pair associated with it, and I have a private certificate authority which I have created using OpenSSL. My private certificate authority also has a key pair associated with it. What I can now do is I can create a CSR, and then my private CA can sign my certificate. Now my certificate is signed by my private certificate authority. But when users want to access your website app1.internal, they do not have this certificate in their trusted store. So whenever your website will be accessed, they will receive a notification on screen that this website cannot be trusted. And you do not want that, because you know the website is trusted and it is a legitimate use case. So how do you go around with that? So what you can do is you can always have automation in place, and that automation can copy this certificate onto the browsers and the OS's certificate store. So for example, if you are in Windows environment, then you can use group policy to upload all these certificates onto the trusted stores of both your OS and browser. If you are on Mac OS, then you can use MDM. With Linux, there is a location where all the public certificates are stored, and you can copy this certificate using a tool like Ansible, and then users can access app1.internal without getting any warnings. And rest of the process is same as we discussed for public CA. The TLS part remains the same. It is just that we have brought in a private CA since our website is internal to the users of our organization. So that's about private CAs. And there are different tools that you can use to create private CAs. OpenSSL is my personal favorite. Then you also have HashiCorp Vault, which is gaining a lot of traction these days. Then there is Small Step CA, AWS Private CA, Cloudflare's SSL, and so on. Offers more control, used for Kubernetes internals, service meshes, and internal HTTPS. And we will be dissecting this point later in this course in Kubernetes internals. So we'll be seeing how private CAs are used in Kubernetes internals. Now let's discuss self-signed certificates. Certificate is signed by its own private key and not by any CA. So as the name implies, a certificate is self-signed. Self-signed implies I created a key pair, and then what I did was I signed my certificate using my private key itself. That is called self-signed certificate. But Varun, why would I do that? So if you are testing your website on a browser, then you might want to check how it is accessible and how it is appearing on the browser. Then you would usually see developers use this. So for example, here I have a developer named Shwetangi. Shwetangi is working on app2.test, and .test is a well-known top-level domain that you can use for testing. And then Shwetangi generated a key pair, and then she signed the certificate using her private key itself. That is why it is called a self-signed certificate. But I want you to understand one thing. These are only used for development or testing. You will never ever see these in production implementations. So whenever a self-signed certificate is presented, you would see something like this on your screen. Attackers might be trying to steal your information from this, because this connection is not private. So you must only use them for development and testing purposes. Not trusted by default, browsers show security warnings. Simple and quick to generate. Example, you can use OpenSSL, Makecert, or Cloudflare's SSL to generate self-signed certificates. I hope now you have an understanding of this. That concludes this lecture. Now that we have built the foundation, in part 2 we will explore how Kubernetes uses mTLS and manages credentials through the kubeconfig file. If you have any questions, feel free to ask them in the comment section and I will reply. If this helped, do consider liking, sharing, and subscribing. It will mean a lot to me. Thank you very much.